Let me start with the very basics of RFIC design. And I think in my last lecture course, when some of the students might have already gone through those courses, for them there will be little repetitions, but there is no way out because those are the newcomers. They will not be, we cannot actually avoid those basic things to go to the more advanced topics. Just before I start my lectures, one of the participants asked me to clarify some of the points on RFIC design, and that too is entirely on the basic part. So I cannot avoid those. So you can relook those who have already participated in my course. And I start the basic low power RFIC design. There are two parts. One is the introduction to RFIC design, and second part is RF transceivers, and then we will go one by one of all the functional modules, starting from the LNA mixer, and then frequency synthesizer, power amplifier, and so on. So if you look at the modern front-end design, essentially if you look at the signal that is coming to your antenna, the range of say 100 megahertz to 10 gigahertz, we call it in the RF region. And the signal comes, and then you need to filter that signal. So you need an RF filters which will actually select the particular band. For example, if you want to choose your GSM band, then 935 to 961, or if you want to choose say Zigbee band, then 2.4 to 2.478 gigahertz. So those bands will be selected. After the RF filters, you know that signal strength. If you look at simple GSM phone, say your signal strength is minus 112 dBm, is a minimum signal. When you look at the tower, if you look at your cell phone, it is at the minimal tower. That means your signal strength is within minus 112 dBm. When you have the full tower, the signal strength is minus 47 dBm. This is the signal strength. And if you look at the Zigbee kind of a protocol or Bluetooth, the signal strength is minus 47 dBm to minus 87 dBm. And what is 1 dBm? If you look at the power level of your input signal, PIN, then 20, if it is in voltage scale it is 20, but if it is in power scale it is 10. Then 10 log base 10 P in divided by milliwatt. Okay, so that is the in the dBm scale. Now those who have the calculator, they can easily calculate that what is the signal strength actually you are receiving. In some case it is nanowatt, and in some case it is microwatt. The kind of signal you are receiving is that, and your antenna efficiency is not 100%. The maximum it can go to 78 to 80%. And after that, RF filter, it's a passive network, maybe 7th order inverse Chebyshev filters having an attenuation say around 14. So definitely you understand the signal that is coming out of the filters, even fraction of nanowatt or fraction of microwatt. So those signals are coming along with their noise. So our challenge is to process that signal. That too at a frequency, say 935 megahertz for GSM or ISM application. or say 2.4 gigahertz for say Bluetooth. So this is the signal that is coming to your antenna, passes to the filters, and it suffers an attenuations. Once it goes there, then you need definitely an amplifier. And what kind of amplifier will be suitable for RF applications? It's a high frequency amplifier, and it also combat the noise already inside the signals or within the systems. There are two kinds of noise are important. One, the signal that is going in EIN plus the noise that is going in from this. So there is a certain signal to noise ratios that is coming to an amplifier. An amplifier would have an own noise that is called noise figure. So that noise also be riding on that signal noise. And finally, after this, it will come with a gain, say around 60 to 20 dB. This particular block is low noise amplifier. This is the amplifier with emphasis on low noise. And its gain is normally, for example, if the loss is say minus 4 dB, then the gain normally of a low noise amplifier is 16 to 20. This is the typical gain. And after that, if you look at the noise figure, this is the gain, that is and this is a noise figure of an amplifier would be around 2, approximately 2 dB. The kind of noise,
and then after that there will be a 20 dB gain. So finally it will be 116 minus 20. So it will be how much? 116 minus 120 plus 20 dB. How much it will come? So 96 minus 96 dBm. And if you calculate that, it will be something like a nanowatt. So the signal that is coming handling is very, very feeble. It is not that very huge signal. And if you look at the minus 47 dBm, that is the highest signal strength, with the minus 4 dB attenuations, that is 51, plus 20, that is minus 31. So it will be few microwatt. So that is the signal that is coming out of your low noise amplifier. But till now, the frequency here is 2.4 gigahertz or 935 megahertz. Here also the frequency is 2.4 gigahertz or 935 megahertz. There is no change in frequency. So when you look at the RF filters and the low noise amplifier, whatever the signal is being received by the antenna, I am not going to have any frequency change. Then people can talk about that once I have a signal, then I can use an A to D converter right after the low noise amplifier. I will digitize the signal and make use of that digital signals for signal processing and extract the voice or my data, whatever signals I like to extract. Then you need actually an A to D converter of 2.4 gigahertz into 4.8 because of the Nyquist criteria. So there will be, if you look, imagine one A to D converter, the maximum frequency is 2.4. Straight away, if you want to convert to digital, then you need a 5 gigahertz, or the data conversion rate will be so high. Is it possible? All of you know that there is every bit there is a conversion of heat, right? That is the heat conversion per bit. So think of it whenever you are actually trying to 2.4 Gbps data is converted to the digital signals, the kind of heat generated will be enormous. If you calculate, it will be, say, 1 picojoule, that is the state-of-the-art A2D converter is 1 picojoule per bit. If you multiply it with that 2 to the power that 2 Gbps, say 16-bit data or 12-bit data, the temperature is nothing but close to the sun temperature. Silicon would not exist. So that kind of software radio, which you call it software defined radio, just after antenna you need a low noise amplifier and then putting A2D converter is not possible. Then what next? So what next is, all of you know that we talked about the heterodyne or super heterodyne kind of a receiver, where you need some kind of a frequency down converter. You understand that why you need a frequency down conversions? Because at that high frequency it's not easy to process it digitally. So therefore next important block is the mixing. We will talk in details about the mixing operations. Now, there is a catch. That mixer is nothing but multiplier of two sinusoidal signals you can have. For example, there are two signals, I will go into details. Two signals, one it is called the RF in, and there is another signal, say, coming from the local oscillator, which is your locally generated, means your receiver is generating that frequency coming from the clock, a crystal clock. Then through a frequency synthesizer, you are generating that local oscillators. Then local oscillator, for example, my voice signal is within the range of, say, 5 megahertz. Okay. So 2.4 gigahertz is my carrier signal. Then 2.405 gigahertz is the carrier plus this. So this is the range, 5 megahertz. This is the frequency range at which my voice signal is carried on a 2.4 gigahertz carrier channel. Then if I introduce a local oscillator of 2.4 gigahertz, what will happen? When you multiply two signals, A sine omega 1t and say amplitude at the same A sine omega 2t, if you multiply sine omega 1t into sine omega 2t, then algebraically we can say that output will be omega 1 plus omega 2 or omega 1 minus omega 2. In this case, when you multiply the omega LO and omega RF, so what is that frequency? Say this omega LO, I say that 2.405 gigahertz, and my local oscillator frequency is 2.4 gigahertz. Then at the output I will get what? I will get two frequency, omega LO minus omega RF, say omega RF minus omega LO, or omega RF plus omega LO. Now I say the frequency down conversion. So I will need a low pass filter to remove that high frequency components. Say it is the low pass filter. So at the output I will get what? 2.4 and 2.405. What is that? 5 megahertz. So that 5 megahertz is my IF band. Right? Now you understand, this can be easily fed to an A2D converter and I will get the digital output. Fine. To get the rest of the signal processing, to extract my voice, data, video, whatever. So that is the today's technology. Now, there are few things are obviously things becoming more complicated, because suppose I am giving a 2.4 gigahertz local oscillator, right? Imagine that signal might leak through my mixer, that is called leakage. That is local oscillator to RF. So LO to RF leakage. The signal might leak through that and passes through my low noise amplifier, and then filter, since it is a band pass filter, so it will definitely pass that signal and it goes to the antenna. What will happen to the antenna? Antenna as if receiving a 2.4 gigahertz signal, and it will then retransmit the same signal in the same path. So what will happen? In spite of 2.405, it will receive a signal of 2.4 gigahertz. Yes or no? The same signal, it is called LO leakage, will pass to the low noise amplifier after leaking through this, an RF filter, it's a band pass filter, and it fed back to the antenna, reflects back to the mixing side. So then what will happen? Your omega RF become 2.4 gigahertz. So then A sin omega LO minus omega RF, that means it is a DC components. So in spite of a 5 megahertz, you are getting a DC level. Zero frequency. So that zero frequency signal, if it comes, then it is an RC filter. I am giving a simple approach. If it is an RC filter, then when DC voltage is trying to charge my capacitor, then the output, immediately capacitance gets charged because of the DC offset. Then capacitance will certainly have more voltage. In spite of the desired signal, we will end up with a huge DC voltage. It will saturate your rest of the signal. So you will never be able to extract any signal. Therefore, people talked about that let us try to make out another approach. What is this? In spite of feeding close to the local oscillator frequency, suppose I am giving 1.2 gigahertz. Then the output will be what? 2.4 minus 1.2. So it will be 1.25, 2.45 gigahertz signal. So it will be 1.25 gigahertz signal. So another mixer, this is called IF1. You are giving, say, so it is 1.25 gigahertz signal, then 1.2 gigahertz signal you are giving, then you are feeding at 0.5 megahertz. So this is two IF stages, right? So this is mixer 1, mixer 2. So this is called heterodyne. Okay. Now if there is a leakage, say 1.25 gigahertz from the mixer, it goes through the antenna to the antenna via the low noise amplifier and the filters. But again it reflects back. But what is the frequency? Our RF frequency is 2.405 gigahertz, but my local oscillator is 1.25 gigahertz, so I won't get any problem. So you can actually differentiate with your local oscillator with the input RF signals. Clear? So that is the genesis of this super heterodyne kind of a receiver. But challenges come where? I have given you the task, say at 1 millimeter into 1 millimeter area, you have to design complete transceivers. So you don't have much area. And not only that, they say that you are giving with a 1 volt battery and your transceivers should work at least 3 years, 3 to 5 years. Very low power consumption for sensor applications. So remote areas, I want to set up one signal, sensors with the transceivers. So that should be able to run the sensors for 3 to 5 years. So typically the power consumption, average power consumptions should be in terms of sub-microvolt, if not microvolt. So think of the challenge of today's, the wireless sensor nodes. That actually emphasizes us to develop a very, very challenging front end, which is the discussion of today's course, right? That how to design a very low power, area conscious, cost effective front end. So 2 points are very clear to you. You cannot avoid the front end just by introducing digital circuits, because the circuit then it will consume so much power, heat dissipations will be prohibitively very high. And second one, you cannot have a super redundant kind of a receiver where hard count, that is a hardware count, is very high. So you have to have those kind of architecture where minimum hardware count is there. And what are the challenges implementing this in RF CMOS? Because while you are implementing all your transceivers inside the silicon, then the main challenge is not the active circuits but the passive circuit. Those inductor, capacitors, transformer, they have a very low quality factor. What is quality factor? It actually tells you how much power is being lost. That is its efficiency. So quality factor of an inductor, for example, is very low, around 3 to 4. But if you want to make a good front-end design, sometimes may require a quality factor 100 or even 1000. If you look at a quartz crystal, the quality factor is 25,000. Whereas an inductor in silicon is only 3 or 4. So think of how much power just getting lost because of the low quality factor. So that is also another challenge. How to make low power, efficient front end with that constraints that the passives would have very, very low quality factor, plus low power, and their modeling is extremely difficult because of the parasitic effects. How these parasitic effects will come into that? Suppose I have to design an amplifier. So I am going into the core transistors. Amplifier, common source amplifier, but definitely known as amplifier is not so simple common source amplifier. But I am giving, there must be an amplifier where I have to put some signals. So suppose the signal that is coming from the antenna after filter is that signal, and I am assuming that the resistance is, source resistance Rs equal to 50 ohm. And that is going to a, I am not going to that stages, and this is grounded. So it is fed to the gate of these transistors. Now from your first year days, you know that if you want to have high gain, at least one point should be sure that your input signal should maximally transfer. That means your source impedance and the load impedance should be matched. Imaginary, that is complementary part with that. In this case, just look at the fallacy. So what is the fallacy? Your source, I am imagining a line. This is the source side, this is the load side. Look at the source side. I have a 50 ohm impedance. Look at the load side. What is that? A transistors. Now with transistors, if you look at least you know there is a gate to source capacitance, CGS. And at least you know there is a capacitance, CDG. Yes or no? But if you look at imaginary right side is purely capacitive in nature, and the left side is purely resistive in nature. So under any circumstances it is not going to match. So the first part that LNA design is at stake. I want to have gain, but my input signal is likely to reflect back. That is the point where the microwave engineers, say 2 decades before when the RFIC design started, even when we started, then the conventional microwave people, they always say that none of your device will work because you are not obeying the Maxwell equations. You are trying to solve by standard small signal analysis based on the Kirchhoff's current law and voltage. This is the problem, because you are seeing as resistive load is feeding a purely reactive load, and the signals will not be maximally transient. So it will be deflected. So now, what we can say that, let us try to make one thing at least. I can put one inductor. Yes or no? What your common sense tells? That I can put one inductor. That inductor, either series or parallel, that doesn't matter, which will negate my capacitance. And the inductor resistance would be 50 ohm. If you look logically, then that 50 ohm will match with this 50 ohm source, and whatever the reactive components will negate the reactive components of the capacitance. So I require an inductor to terminate that source. But if you have a look at an inductor is not an ideal inductor. I say quality factor is very poor. What is quality factor? Q equal to omega L by R. All of you. So quality factor poor means R is high. That R is basically in series with. I am talking about that series resistance. But why do you have those inductor? Inductor in a coplanar inductor is like that. So there will be a current flowing to adjacent block. So there will be a capacitance. Yes or no? So those capacitance will come over. So think of it, when I am introducing an inductor, unknowingly I am also introducing a capacitor. Yes. Then who will negate that capacitance? Again, this capacitance will be added to my CGS. So it is an egg and chicken problem. For that, to negate that capacitance, again you have to put one inductor. Inductor would have a parasitic capacitance that will be added to your CGS. So this is not the equation which is going to converge. Okay, you need some kind of optimizations. So that is the challenging task. So you need iterations, very long iterations to make, but finally you are getting maximum power transformation. If you look at the practical sense, you are measuring a two-port model, the scattering parameters S11, S22, S12 and S2. Okay? This S11 I am talking about, right? The input reflections, S11, you need minimum at least minus 20 dB. How minimum? Minus 16 to 20 dB minus. So S11 exactly matching 50 ohm, no reflection. That means infinite. Okay. But it is not possible. You will always get physical values 49.7 like that. So I would say that correspondingly you will introduce some kind of S11 of minus 16 to minus 11. So that is a very practical feeling you will have. So same thing also comes in the output. When you take the output, you are also having a load 50 ohm. But again those capacitances will come and you have to negate by a matching method. So that's the challenges of any front-end design, where the parasitic impedance are becoming the major challenge to overcome. So if you look at the RFIC design in one sentence, that it is nothing but a parasitic aware design. Parasitic aware. If you are not aware of the parasitic effects within the passive components or within the device, your design would not be complete. You might get a very exotic results in ideal case, but that is always frustrating, because if you look at these parasitic effects, your gain, your noise figure, your actual results will suffer from the simulation data. So let us come into the some of the basic things of RFIC, that where you will tell it's an RF or it is in the domain of our interest, disappointed. So if you look at here, the frequency that is starting from 100 megahertz to 10 gigahertz, that region is called the RF region. So I say that if you look at the wavelength is from 3 meter to 3 centimeters, what will happen in this case? Let us try to understand the phenomenon. Suppose this is a periodic signal. Okay? And I have one small component is this. So what is this? 0, pi by 2 pi, 3 pi by 2, 2 pi. This is the phase angle phi. So look at this, if the component size is here, and if you look at the change of the phase, almost negligible. Yes or no? The change of phase along the length of the component is almost negligible. When a voltage is flowing through a resistance, is there any change in phase? The current and the voltage are in same phase. But whenever a voltage is fed, AC, is fed to a capacitance or an inductor, what will happen? You will see that your voltage and current, one case it is phase lag, other case it is leading. So look at the scenario that when the component size is this, bigger size, what will happen? Along the length, what you are seeing, there is a change in the phase. If there is a change in phase, who is responsible? You just immediately know, resistance is not going to change the phase. But whenever there is a capacitance and inductor, there is a change in the phase. So a simple conductor would not be a simple conductor. It will be a combination of LC network, that is the transmission network. So in spite of that, you will get a simple inductor, a simple conductor is becoming a transmission line. Right? So like that. So now you understand why this parameter is known as when the component size is smaller compared to the wavelength of the propagating, then we call it lump parameter. Whenever you bigger size, there is an appreciable phase change along the length of the components, then you have a distributed model. So there are two things. Let us come into the points. What I have said that you can make this point. Why the lump parameter model fails? You know the answer. When the frequency increases, wavelength is reduced. When the wavelength is reduced means the length of the components is comparable, then there will be an appreciable change in phase along the length of the components. So that requires distributed model. Next question comes, all your device equations are small signal AC analysis. All Kirchhoff's law, GM pi model, these are basically nodal equations. You solve the current nodes or closed loop voltage across the closed loop is 0, or current node where the source and sink, it will be 0, sum total of the currents. So those models are used. And most important, the third one, all your impedance, that is Z parameters, 2-port, 4-port network, A, B, C, D parameters, Z and Y, those are not going to work in RF design at high frequency. What you have to do? You have to go for scattering parameter or S parameter values. But Again I say, there is no such equations exist till that which solve my RF solutions using Maxwell's, especially for RF design. All are basically cadence, mentor graphics. They are basically small signal AC analysis, not based on the Maxwell equations. Again, those conventional microwave people, they will put a bang on it. Hey, you are using those equations. Those equations are not valid at high frequency. How do you work with them? My answer is pretty simple. There is two fundamental laws. They don't clash each other. They always converge. But you have to understand that point of convergence, where they converge. Where philosophically you have to understand that where these two equations or two thinking process, one is the Kirchhoff's current and voltage law, and other is the Maxwell equations when they are converging. Let us try to bring that point very clearly. That will answer these questions, especially for RF. If you look at those Maxwell equations, nothing but sets of four equations. Divergence of electric field is rho by epsilon, nothing but Poisson's equations. The second one is divergence of B equal to 0. Magnetic flux is 0, that is monopole cannot exist. And the third one is curl of H epsilon d dt plus J is the third, and the fourth is curl of H equal to mu G, is Ampere's law. Right. So those four equations are set of equations in Maxwell's. Yes or no? All agree? Now I am asking you to imagine one simple statement. But suppose this is the velocity of electromagnetic wave in free space. C equal to 1 by square root of mu into epsilon. What I say that, suppose this is the velocity of the electromagnetic wave, and this is epsilon and the mu. What is epsilon? Permittivity, and mu is permeability. So if any one of them goes to 0, then my C eventually goes to infinity. Can it go to infinity? Because relativistic mechanics, that tells you the velocity of light cannot exceed the velocity of light. Nobody can exceed the velocity of light, right? That is a max velocity. So that is the velocity of light. But the point is that, imagine that if epsilon and mu tends to 0, I am going to that infinite velocity. Suppose an electromagnetic wave is, after it is passing through the antenna, this in free space, it goes to your system and passes through the device. It is basically silicon. And I said that at 1 gigahertz, 100 megahertz to, this is 3 meter to 3 centimeter. That is 10 gigahertz, that is 3 centimeter. What is the dielectric constant of silicon? It is 11.78. Make it 10. So 3 centimeter, make it divide by 10 equal to 3 millimeter. Then if there is a lump parameter model and the distributed parameter model, if you think that when the component size is 1/10 of this wavelength, then actually the lump parameter model started to fail. So 3 millimeter, 3 centimeter, 3 millimeter, 0.3 millimeter. So that is the point at 10 gigahertz, I will be concerned that my lump parameter model is going to fail. Why? My wavelength, phase distributions, and the component size, you will have an appreciable phase difference. So that point I have to look into. But look at here, 0.3, and what is the device size? What is the device size? Source to drain length, nowadays 65 nanometer, and I am talking about 0.3 millimeters. So you understand, I am lucky that my basic Kirchhoff's law based, the small signal AC analysis is still valid in this small, because my device size is very small. This proves that I can use the lump parameter model. Next question, can I use the Kirchhoff's current law and the voltage law? Now I say that epsilon tends to 0. Now you yourself can tell that if you look at the equations, curl of H equal to epsilon V dt plus J. Now if any of this epsilon, say epsilon tends to 0, so this part will be 0. So curl of H equal to Z. Now take the divergence in both the sides. The divergence of curl of H equal to divergence of J. What is divergence of curl of H? Vectorial calculus. What this means? 0. Divergence of curl. So what is divergence of J? 0. What is divergence of J? 0 signifies if there is no source and sink, the current at any particular node is 0. All the sum total of current I1 plus I2 plus I3, there is a divergence, and that will be 0. So I am arriving into the Kirchhoff's current law straight from the Maxwell equations, but understanding the scenario that the velocity is infinitely high. It is not infinity. Infinity is relativistically round, close to the velocity of electromagnetic wave, and that is exactly happening in case of silicon. So you can yourself can prove the fourth law. There is curl of E equal to mu dH dt. So mu tends to 0, so curl of E equal to 0. What is curl of E? E dot dl line integral? Yes or no? So E dot dl line integral, right hand side equal to 0 means what? Electromagnetic force, EMF, that is the voltage around a loop, in a closed loop, this is 0. So that is Kirchhoff's voltage law. So you understand two fundamental laws, they are not clashing each other. Under the special circumstances, which I have explained, what is the special circumstances? They are actually convergent. So there is no point of any contentions or any kind of a confusions that you have to use the Maxwell equations while solving the current voltage relations in a small device which size is few micron or nanometer, and where the velocity is close to the velocity of light. Am I clear? Everybody have understood this? So that's the things you have to understand in RLC. But when I say that the electromagnetic wave, that is my signal, is not going to my device straightway. It is coming, it is captured by the antenna. It is processed through the filters. So those filters and antennas are not nanometer or micrometer size. Yes or no? They are size of centimeter or millimeter. In that case, the wavelength is comparable to the size of the components. Then the phase difference would occur across the length of that. In that case, you have to use the Maxwell equation based solutions, HFSS, I3D, ADS, Microwave Studio, all those 3D or 2.5D softwares. So I say that from antenna up to the device, all Maxwell, but from Maxwell to Kirchhoff's current law and voltage law, especially small signal AC model, go to the device. Again, when it goes to the component size in filter, you have to go for 3D or 2.5D centimeters. So this point is clear. So you should know about your boundary, where you have to solve which equations and get the right answers to this. Clear? Now come to the next points.
In the previous slide, you were saying that you are trying to equate the permittivity and permeability to 0. So what is its equivalent analogy on 0? They are not really 0.
There is no equivalent analogy of that, but only analogy is that their velocity is enormously high. C tends to infinity. Infinity means C tends to C. C, velocity of light, 3 to 10 to the power 8 meter per second, that is the max. So almost similar velocity it is propagating to 0. So you can say in that circumstances your epsilon value almost 10 units per second.
That means the circuit speed, intrinsic speed of the MOS transistor is very high.
Very high. That is
the-
but you cannot exceed the velocity of light.
That is the fundamental distinction.
Restriction. That's why very, very high. That is the reason why you can actually see that. questions. I like questions. If you have any questions, you can ask. Fundamentals. Okay? So that is the bottom line. You can look at here. For on-chip design, you can use the Kirchhoff's law, but when you are off-chip or those components, you can go for the Maxwell equations. So how your parasitics will, a conductor will be a ladder network of inductor capacitors, and the capacitors will be a series combination of inductor, resistance, capacitance and resistance and so on. And the inductor is inductors and resistance in series and the capacitance in parallel. So that will be a nightmare for you, because an inductor is not an actual inductor, it's basically a capacitance. Even some students designing an LNA at 65 gigahertz just tell me, sir, all my inductors becomes capacitors. It will happen, because if you do not understand the self-resonance frequency, what is the biggest problem here? Look at here. When an inductor having a capacitor, I am giving a simple case. Suppose this is an inductor. In your mind it is an inductor. But parasitic, there is a capacitance. Yes or no? Look at that. So now think about, I am looking at the impedance from this side. Now if you plot the impedance versus the frequency, what will happen? At zero frequency or near zero, it will behave as an inductor. So your impedance will go up. Then what will happen? If you go on increasing the frequency, it will go up and then swing to a very high level. This is known as the resonance frequency. After the resonance frequency, what will happen? It will behave as capacitance. So think of it, this is the frequency which is called the F self-resonance frequency. So if you are designing something where the self-resonance frequency, because of this LC network, you are not aware of this capacitance. So your impedance, whatever you are thinking of the inductive one, will be basically a capacitor. So maybe your self-resonance frequency of that inductor was 25 gigahertz and you want to work on terahertz. So the inductor will behave just as a capacitor. So that kind of confusing state will come while you design. Negative value will come. And you have to be aware of that parasitic effects. Okay?
How do you resolve this issue of
Yeah. In 65 gigahertz, first of all, the cutoff frequency of your transistors should be as high as possible. And then I will go to the silicon process probably to be better for you, but just I will tell you that there is a special substrate. A normally high resistivity substrate is used to improve the cutoff frequency of the transistors. So you should have at least the cutoff frequency of transistors 10 times higher than the operating frequency of that. Second, all the components which you are trying to incorporate in your design, its self-resonance frequency should be as high as possible compared to the operating frequency. Then you cannot design. So those things are pretty important. You have to find out what is the, in case of transistor, what I said, the cutoff frequency. Cutoff frequency means the frequency of unity gain band. And the self-resonance frequency, just as explained. So those frequency are the limiting factors. So you should make your operating frequency 4 times or 5 times, not even 10 times less than that. Suppose 2.4 gigahertz, then your cutoff frequency should be around 24 gigahertz. So you need a special transistors called RF transistors, where the substrate resistance is very low. So this picture is clear to you. So you need from the null parameter to the distributed parameters, and where you actually want this. Secondly, how it differs from the analog design to RF design. In RF design, there are few things that will come line by line, but let's come to the analog design, where the frequency is less than 100 gigahertz. Suppose I design an amplifier. then in an amplifier you must be talking about the gain. So the small signal AC analysis is good enough. You know that GM into RO. There is a gain, intrinsic gain of an amplifier. What is G? There is a transconductance. What is R? That is the output impedance. That is small signal analysis. So intrinsic gain divided by the attenuation is give you the gain of the amplifier. If there is a source degeneration and so on. So small signal AC analysis is good enough. Next important part is the linearity. Now what is that linearity? A linearity means that suppose I am feeding one signal, say 2.4 gigahertz. I like to get 2.4 gigahertz at output. But how will you ensure? As long as the device behavior is linear. But all you know that any semiconductor is nonlinear in nature. IV characteristic itself is a exponential characteristics. And if it is exponential characteristics, I am giving an input periodic signal. You look at here, definitely it will give the nonlinear output. And nonlinear output introduces what? Harmonics. So 2.4 I will get 4.8, all those second, third, fourth, fifth harmonics. And those harmonics are nothing but introduce the distortion in your output signals. Now, while you talk about the linearity, then the most important part is how this exponential relationship will be linearized. What do you do actually? You introduce some kind of a biasing voltage. What do you mean by biasing voltage? It's called quotient pulse. So you actually bias it, and then your input signal is very, very small around that biasing point. So within that, what is that? Suppose I am giving 1.2 volt quotient voltage, and I am varying the voltage, the input signal in microvolt. Think of it, within that quotient point the variation is few microvolt, 100 microvolt. Then that is called piecewise linearization. So I do not consider any kind of nonlinearity within the exponential zone, a small part. Mathematically, what is that? Suppose that e to the power x is 1 plus 1 by x plus 1 by x, all these parts, x square factorial 2, x cube factorial 3. So I am introducing that linearity means I am actually negating all those second order and third order. So physically you have understood what is the linearity, and also mathematically you have understood what do you mean by linearity. But can you tell me why the device is exponential in nature? Simple questions. Why suddenly it becomes exponential in nature? Do you know the answers? Very simple. Electron energy distribution is Maxwellian in characteristics. So that's why all your IV characteristics are linear in nature. Is it clear? Only in the first order approximation you are basically linearizing that form, which assumes that your input signal to the gate of the transistor is very, very small compared to the bias. If you have any confusion, you can. So this is linearity. So linearity, if it goes to the nonlinear region, that will introduce harmonics. Now if it introduces the harmonics, what will happen? Suppose there is one signal that is one spike, but if you have more number of spikes, I am talking about the spectrum, this is the amplitude. So this is called Scott. But conservation of energy tells us what? Energy is fixed. Now because of the nonlinearity of the systems, energy is now distributed along all the spectral components. What will happen? You require your fundamental components at the cost of your fundamental components. What does it mean? That the gain of the system will be lowered. So, if you look at an amplifier, linearity and nonlinearity, what will happen? This is my input and this is my output. So initially when it's a linear region, I need some kind of a linear gain, right? After that, what will happen? It will be lowered or it will be going up. Conservation of energy tells us amplitude will lower down because the energy will now distributed across other harmonic components. So in spite of going into the linear path, it will now drop. That is the nonlinear. This is the linear region. After that, the nonlinearity part will come. So that nonlinearity part means here harmonics are created and energy get distributed about other harmonics. And we will define that if at what is the input level for which there will be a compression of the expected output when it is a linear, that V in is known as 1 dB compression. So that is the linearity of the systems. What is the next point? Is the stability. A very important features in stability. Everybody says that when you first time started designing an amplifier, you will end up with an oscillator. Or vice versa, when you try to design an oscillators, you will end up with an amplifier. Why this kind of oscillations you don't want? Because suppose you are designing an amplifier, going to a simple core state. So this is my input and I am getting the output. Okay. Now what is an oscillation? Oscillation means when a fraction of the output that is fed back to the input and added constructively, not destructively. Then at certain conditions called Barkhausen criteria, the system itself starts oscillating without requirement of external signals. I made a story out of that. Let's go to some kind of a lighter one. Say one student used to work in an engineering college, okay? And he used to get 2 rupees from every day from his father. And within this 2 rupees, he buy train ticket coming from Barashat and going to Jagatpur University. So whatever money is left, he used to use that money for buying his tiffin, means the after classes and the this way father is giving money to him and he goes to the college and comes back. Then one day you find that in the train compartment, somebody is playing card games with money. And he is an engineer, must be more intelligent. He said, okay, this is a very good way. Let me try with my luck. So he's invested that 2 rupees, whatever money of minus the ticket price. Then he owned the pen. So he is getting money. In that way, finally, what happened? That his father is noticing his son is not asking for any money. 2 rupees, even 50 paisa is good enough, because he is able to multiply that money. And one fine morning, his son is saying last 2-3 days, not even bothering about fathers to ask him money. That means he is self-sustained. An oscillator is like that. Then somebody say jokingly that even that 2 rupees, father didn't give the money, he actually got it. The noise. So that's the way how the oscillation builds up. So the noise that actually responsible for noise, even for fraction from some balance or lose money, he gave that money and finally builds up that through gambling game and finally get unsustainable way of living, going to the college and having food and so on. But an oscillator, Barkhausen criteria tells that you don't need any energy like that, but that is basically ideal case. If you exactly satisfy the Barkhausen criteria, then you know that oscillation built up will be few nanoseconds, after that the oscillation will stop. You need some additional energy to feed. So your A beta is not equal to 1, a little bit high, and then A beta is what? You remember the beta factor, right? So that little bit high you have to give and then you have to reduce it like that. So that's the story, that how the oscillations will start the from stable oscillation comes over here. And then stability will come because you look at output, this is the capacitance. So the output might, there will be fraction of the output from here will feed back to the input, and there will be an oscillations like that. So what is the culprit for oscillation? It's C, this is the drain, this is the source, this is the gain. So C, D, G. So a fraction of the output that will come where this capacitance and this. So you have to find, so you may not be knowing that parasitic capacitance, but that is the finite capacitance which actually tells you that some kind of an oscillations might build up. Stability, no oscillation, or oscillation with fixed amplitude. In this case, it is going to the unstable state because my amplifier would have a fractional output come back to the input, and that will make the oscillation. Right? It may die down, but again it builds. So this is called the stability. So it is knowingly or unknowingly it will have through the parasitic part. Knowingly means you remember that you have a resistance or inductance at the source. You know that there is a negative feedback that first year classes. So that feedback will come to your input. So there will be a known path of feedback. So those will create the instability into the systems. So S is the stability parameters that should be greater than 1. An amplifier, when you talk about linearity, like 1 dB compression, gain like dB, there must be a stability calculations. It should be as high as possible, right? And that will not come freely. So you have to compromise with something. Then in the noise, which requires a lot of discussions. So I will stop for 5 minutes, right? 5 minutes is okay? Then I will, because this lectures is getting videoed, so 1 hour is the maximum capacity of the cassettes, right? So you change the cassette now?